Hello, I'm Attila Keresztes, a research scientist at the Ötvös Loránd Research Network, known until 2019 as the Hungarian Academy of Sciences. In this talk, I will like to show you work that highlights the advantages of using high-resolution magnetic resonance imaging to better understand the neurocognitive development of memory in humans. Here, on the left, you see Henry Malaysia, a famous patient whose epileptic seizures were meant to be controlled by surgery, removing almost the whole of his bilateral hippocampi from his brain. Consequently, he lost his ability to recollect events happening after the surgery, but had no trouble learning skills such as drawing only seeing his hand and his drawing from a mirror, the so-called mirror drawing task, yet having no recollection of learning events, such as learning this task with a particular person. Among others, these discoveries led the neuropsychologist studying Henry Malaysia, Brenda Miller, to the conclusion that there might be multiple memory systems. She conceived of declarative and non-declarative first. But on the right, you can see the current mainstream taxonomy that has unfolded during the following decades. And this taxonomy still guides most research today about human memory. Now here's a small advice from the then 101-year-old Brenda Miller. Lynn Nettle asked her what advice would she have for someone who's starting out their career now. What kind of problems should they look at? And Brenda Miller said that she wouldn't think of it in terms of problems so much as getting aware of different technologies. And I think it's different methodologies, including behavioral ones, of course. But what you could learn from what I call behavioral neuroscience is most people call cognitive neuroscience. This is what, to me, has been so exciting, that you can look at the living brain in action. And in this talk, I would like to show you specifically what high-resolution structural imaging of the living human brain can add to research on human memory development. On the left, you see a coronal slide showing the medial temporal lobe of one of our participants, with the standard resolution T1 NP-RAGE that is used almost by default in all MRI research to image basic human brain anatomy. On the right, you see a high-resolution image of the same region in a different participant. Now, these techniques have been now around for more than a decade, and they are really easy to implement using standard 3D scanners. Importantly, these high-resolution images allow us to visualize landmarks within the hippocampal formation that we can then use to establish reliable and valid methods to delineate subfields within the hippocampus. This can be done fully manually, like here on the left, but can also, so modern machine learning-based algorithms allow us today to build atlases of our own segmentations and apply those to novel brains to segment. And here's one of our attempts to show very high consistency between our own manual segmentations and automatic segmentations of the same brains using our own atlas built from an independent set of brains using the automatic segmentation of hippocampus subfield software. I want to highlight the 4 subfields on this slide already that we measured in all the studies that I present in this talk: the entorhinal cortex, the subiculum, the dentate gyrus CA3, and with green, the CA1-2 regions. Importantly, the dentate gyrus and CA3 cannot yet be validly and reliably delineated from each other using these images. Therefore, it is standard practice to lump them together, and the same goes for CA1 and 2. So why look at different subfields within the hippocampal formation? Well, one novel direction since the conception of the classic taxonomy of memory systems based on neuropsychological findings comes from computational models of human memory from the 60s and 70s already. In these models, corroborated by animal findings, neurocomputations of pattern separation and pattern completion support and contribute to memory processes. Pattern separation by orthogonalizing highly similar inputs to the hippocampus, and pattern completion by auto-completing partial neural inputs to the hippocampus. Importantly, the subfields within the hippocampus have specific contributions to these processes, with the dentate gyrus and CA3 region cytoarchitectonic properties allowing this region to pattern separate, and the CA3 and CA1 to pattern complete. Pattern separation may support thus instances of memory when you need to differentiate highly similar memories from, for example, where I parked my bike this morning versus yesterday morning. And pattern completion may support recollection of full information based on partial cues, such as connecting a name to a face, or also potentially to construct general memory representations. And why study hippocampal subfields and hippocampal computations in research on human memory development? Well, first, already studies using standard resolution MRI, most importantly by Nitin Goktai in 2004 and 2006, hinted at the possibility that the hippocampus develops later than previously thought, and development may follow different maturational tracks across different regions within the hippocampus. Importantly, when looking at total hippocampus, alone would mask this heterogeneity. More recent data from rhesus monkeys suggest that development of subfields of the hippocampus is ongoing until potentially late into adolescence. And here you can see, for instance, the dentate gyrus and the CA3 in cohorts of age groups, showing a more steeper maturational profile than the other subfields. Second, observation of overgeneral memories in children are dating back to Swiss developmentalist Jean Piaget, and this is still an open question whether differential maturation profiles of hippocampal subfields relates to the maturation of pattern separation and completion, potentially providing a part in mechanistic explanations of child memories becoming more and more specific in development. So in our first study I presented in this talk, we asked these specific questions. Do human hippocampal subfields show heterochronous development? If yes, is structural development related to development of subfield-specific hippocampal computations? So the first study from a different lab that looked at structural development of hippocampal subfields in children aged 8 to 14, here on the left, showed that indeed there were age differences in specific subfields, including the dentate gyrus CA3 and CA1 regions. In our study, summarized here in this larger figure on the right, we found heterogeneous maturational profiles for the 4 subfields we studied. So these are shown here. And this was mainly driven by an increase in dentate gyrus CA3 throughout the sample from 6 to 14 years of age and then into adulthood. We linked this pattern of subfield maturation with a multivariate score that expressed this multivariate maturational profile to task performance, and specifically we found that the hippocampal maturation was linked to mnemonic discrimination ability. The task we use to measure mnemonic discrimination is depicted here. It's called the mnemonic similarity task, and in this task participants incidentally encode images of objects, and then at the surprise recognition task they are shown in identical or highly similar images as well as novel foils, and they have to indicate for each image whether it's an identical to a target or it's similar to a target or it's a foil. And their ability to discriminate highly similar memories was indexed by a Lure discrimination index that we calculated based on the proportion of similar responses to lures like this. In a follow-up theoretical paper written together with Nora and Zoe, based on their very similar finding of ongoing improvement of mnemonic discrimination using a very similar mnemonic similarity task between ages 4 to 6, and the contrasting result of adult-like relational binding in the same sample, as well as based on data showing that spatial resolution, spatial mnemonic discrimination ability increases in children aged 1.5 to 4 years of age, we hypothesized that maturational differences among the subfields within the hippocampus may contribute to the developmental lead-lag relation between specificity and generalization. In another study I would like to highlight in this talk, we looked at the vulnerability of hippocampal subfields in face of stress, and how any stress-related effects on hippocampal subfield development may affect memory development. So the motivation was as follows. We know that the hippocampus is vulnerable to adverse influences during development, and we know that one of the primary sources is stress, and there are plenty of observations showing smaller volume in especially adults with history of childhood abuse or maltreatment or excessive stress in their early life periods. But the potential mechanism may be that the glucocorticoid secretion or sensitivity potentially in dentate gyrus and CA3 is driving these effects. So one hypothesis that has been out now for quite some time is that chronically elevated levels of cortisol may have negative effects on hippocampal development that may in turn lead to memory impairment. But the results are mixed. So most studies are retrospective, as pointed out, and only a few studies with healthy children were conducted and provided mixed results. And most of those looked at hippocampal volume, total volume. So in this study, we asked whether accumulated levels of cortisol are associated with decreased hippocampal subfield volumes. And if yes, is that association specific to the dentate gyrus and CA3 region? And does that association manifest in behavior? We used hair cortisol to assess cumulative cortisol concentrations using a 3 centimeter long hair strand. And based on average hair growth, that allows estimation of cortisol accumulated during the 3 months prior to testing. And here we use structural equation modeling to account for measurement error in subfield delineation, expressing subfields as latent variables with left and right hemispheric indicators of hippocampal subfield volumes. Importantly, we found, as hypothesized, a negative relationship between volume of dentate gyrus CA3 and hair cortisol, and this was specific to this subfield. However, even though this association has been already an independent replication of a concurrent study by Mertz et al., we did not find associations between subfields and memory tasks assessing either mnemonic discrimination or associative memory or spatial memory. Therefore, we could not go on testing whether cortisol effects manifested in memory. So additionally, we did not find associations between stress and cortisol, and as a great review from Bruce McEwen details this, it is not that surprising given that the complexity of cortisol effects and its relation to stress. In brief, these results do suggest that dentate gyrus and CA3 is specifically vulnerable to cortisol effects. However, the effects implications are yet unclear, and it may be, for instance, that such cortisol-related brain effects only manifest in behavior after longer exposures or more severe exposures. And so not only for this, but for more important reasons as well, longitudinal studies are needed. One of the main reasons is that data on hippocampal subfield development is mostly cross-sectional, except for 3 studies that we know of, and these provided mixed results. Theoretical accounts, importantly, and simulations and comparisons of cross-sectional and longitudinal analysis of the same data do caution already strongly against making inferences about change based on cross-sectional studies. So in a longitudinal follow-up of the previous study, we asked whether hippocampal subfield volumes change after 6 years of age, whether the pattern of change agrees with age associations in cross-sectional studies, and whether volume is associated with memory. Just to highlight the nice consistency across our own and other cross-sectional findings, here I show you that we found in both waves that age was positively related to dentate gyrus CA3 and CA1 volume, but not with entorhinal cortex and subiculum. And I have to say that only these associations were significant. This was a trend-level association. This was non-significant. Here again, we assess change using latent change score models, which in addition to estimating a change score, provide us with 2 additional parameters of interest. One, variance of change, and the other is covariance between change and initial values. And in this study, we also used versions of these models where hippocampal subfields were expressed as latent variables, wave 1 and wave 2, using hemispheric indicators of left and right. And this is, I believe, one of the most striking findings I've seen recently on hippocampal development. It actually should not come as a surprise, given the intro slide for this study cautioning against inferences on change based on cross-sectional data. However, it is striking to see it. So in these quite dense figures, each dot represents, I'm going to walk you through this one, each dot represents one participant's data, volume data at one wave. And the blue and orange lines represent individuals showing an increase or decrease, respectively. Whereas the middle line shows average change. The two black lines show cross-sectional age associations at wave 1 and wave 2. And L denotes significant longitudinal change, and C denotes significant cross-sectional age effects. And it immediately comes to the eye that there is almost no overlap between cross-sectional and longitudinal effects. Especially, importantly, only CA1 and 2 and anti-GIS CA3 show cross-sectional age effects, positive age effects. And only subiculum and entorhinal cortex show longitudinal change. For entorhinal cortex and CA1-2, there is also a disagreement in the direction of the change and the cross-sectional age effects. In addition, we looked at change associations and found that change in subiculum volume was associated with change in spatial memory performance, a positive association again. And importantly, we did not find such associations between either mnemonic discrimination and subfields or hair cortisol and subfields. So in summary, I've shown you that patterns of cross-sectional age differences was linked with pattern separation completion bias in children aged 6 to 14 years of age. I also showed you that the hippocampal subfield's dentate gyrus CA3 was specifically associated with accumulated levels of cortisol assessed from hair in 6 to 8-year-olds. However, I also showed you that cross-sectional age associations and longitudinal developmental trends in hippocampal subfield volumes were highly discrepant, both by subfields and in direction. And I have to note for future research that the subiculum was the only subfield that showed consistent age differences and change. And the subiculum was the only subfield showing brain cognition change associations. In addition, I hope I managed to highlight that novel high-resolution magnetic resonance imaging techniques can provide important insights about hippocampal development. I also hope to have managed to highlight that we need caution when interpreting cross-sectional data, and also that cross-sectional and longitudinal data can complement each other. So I think it's a nice idea to always publish cross-sectional age associations whenever publishing longitudinal data. And I just highlighted with red that longitudinal data is needed to understand development. To end with highlighting challenges, pitfalls, and potential future directions, I want to just show that there are plenty of software tools and novel efforts to assess power of longitudinal data, longitudinal studies, and to have as large samples as possible using consortia efforts. And also wanted to highlight that it's really a nice idea to, if you go for the longitudinal effort, to have not only 2 but more measurement time points, as using more you can assess nonlinear change as well. And for the future directions, I want to highlight that we just need more longitudinal studies. And I also want to highlight the work of Cameron Ellis and Victor Brown using infant fMRI, which is a really promising direction, which just highlights that this is possible. And it would be really cool to see studies in the future that use functional MRI in longitudinal data settings. And with that, I want to thank you for your attention, and I want to specifically thank Marcus Berklabagna, Yili Shin, Drew Bender, Laurel Raffington, Zoe, and Nora for their contribution to the studies and the ideas presented in this paper, and also for inviting me for this symposium. And I want to also thank Roman Lindenberger and Kristin Heim for their support in this work. Thank you for your attention, and I'm looking forward to your questions.